Hi, in this video I'm going to go over how to answer Achievement Standard 91391 paper, demonstrate understanding the properties of organic compounds from 2023. Okay, so let's get started. Right, question one. So if we look at question one from the paper here, we can see that part A here says 2-hydroxybutanic acid exists as enantiomers, which are optical isomers. That's the name for the two optical isomers that you might have. And then they've given us a structural organic molecule, the structure of an organic molecule. And the first thing they ask us to do is circle and describe the features or the structural features that enables 2-hydroxybutanoic acid to exist as enantiomers. Okay, so if you've done your study on enantiomers, you know that the most significant property that they have that makes them be an enantiomer is they have a chiral carbon, or a carbon that has 4 different groups or atoms, that is substituents, coming off it. So in this molecule, we can, if we look at the very first carbon, we can see that it has 3 hydrogens. Those are identical, it can't be chiral. The second carbon has 2 hydrogens coming off it, so it cannot be a chiral carbon. The last carbon has different groups coming off it, but if we remember this is a carboxylic acid group, one of the groups is a double bond oxygen. It only has 3 groups atoms in total coming off it. However, the third carbon from the left here, it has on the left a CH3CH2 group, on the right a COOH group, down the bottom an OH group, and a hydrogen atom. It has 4 different groups. That there is our chiral carbon, so we circle that one. Now remember what I said that made it a chiral carbon is it had 4 different substituents. Now you might just use the words group or atoms, or atoms/groups attached to it. Now we have to draw the enantiomers, or the 2 versions of this. The way that I find easiest to draw this is to try and draw a 3D representation. So here I've drawn a 3D representation. Now even though I have bolded in one of the bonds coming out towards us, and I've kind of dashed the one going behind us, they can all be straight lines. But what's important when we draw this molecule is that we ensure that we show that there are 109-degree angles, right? So we kind of want to draw it. So if I was to draw this molecule and draw it at 90-degree angles, I would get this wrong. So I have to have an attempt at representing a 3-dimensional shape here. So I just draw one of them with showing the 4 groups. Okay, 1, 2, 3, 4. And then what I do is I just draw a mirror plane, or a dashed line in between them, and I draw a mirror image of the other one on the other side. And that way I know that these two are what are mirror images of each other, enantiomers, and are the 2 versions. And that's how I would suggest that you should draw these molecules. Okay, so how did they mark this? Well, if you were able to circle this and recognize that this is a tetrahedral arrangement, you get an achieved. If you were able to describe the features, that is, it has 4 different substituents, 4 different groups atoms coming off the carbon, and you're able to draw the 2 representations, you get a merit. Hey, that's a nice start to the paper if you have covered your enantiomers. Okay, so B is they want us to devise a reaction scheme, show a series of reactions to convert pentan-2-one into pentyl ethanoate. We need to include the reagents and conditions and the structural formula of the organic product, or the organic products in each step, I would say. So here is a picture of the molecule that we need to show. This is pentyl ethanoate. Now we need to look at it, and we need to ascertain, work out what are the actual final molecules that are used to create this ester. So an ester, remember, is when we take 2 smaller molecules, we add concentrated sulfuric acid, and they connect together to make an ester bond. We lose a water in the process. On the right hand side, this pentyl group has originally been a pentanol with the alcohol group off the first carbon, and the NO8 group hasn't originally been an ethanoic acid. It could have actually been an acid chloride as well, so we'll talk about that when we get to the space. Okay, so we need to start, however, with pentan 2-one. Now this is the part of the ester molecule that had 5 carbons in a row, but what we can see is the functional group is coming off the second carbon. In order to make the ester, the alcohol group has to be off the first carbon, so we need to move this group from the second carbon to the first carbon. Now the way that we usually do this is we do a series of elimination and addition reactions, but in order to do an elimination reaction we need to convert this functional group, this carbonyl functional group here, or the ketone functional group, into an alcohol functional group. So first step is to reduce this by adding sodium borohydride. Okay, and then once we've reduced this, we've turned it into the alcohol, pentan 2-ol. So this is cool. So now what we want to do is we want to turn this alcohol into an alkene, okay? But we want the double bond on the left-hand side. So in order to turn an alcohol into an alkene, we need to add concentrated sulfuric acid. Now, notice that my sodium borohydride, I've put the conditions I've added here, that is actually dissolved in alcohol. You must really get away with not putting that in there, but with sulfuric acid you have to write concentrated sulfuric acid. Those are the conditions of the reagent, so the condition and the reagent. So we add that and we get the double bond on the left hand side. Now if we remember Zaitchev's rule, we know that this is actually the minor product. So I've just gone ahead and written it here. They haven't asked me to, but what if they're going to mark based on that? I'm just putting it there anyway. So now what we want to do is, okay, remember looking at the top, this is the product we need to make. I need a alcohol group coming off the first carbon, so I'm going to add water. Now there are many ways you can show adding water. You can put H2O/H+, you can put H2SO4/H2O. I just like to put H2O/H+. Add the water. Again, this is Markovnikov's rule. The major product would be when the hydrogen is added to the first carbon and the OH is added to the second. So this is a minor product again. Both of these are the two minor products that result from these reactions, but we can still separate them and collect them. And then we're needing to make the ester. Well, we're either going to, there's two options here, both are valid. I'm just showing one. So here I'm going to add ethanoic acid, right? And it's when I add ethanoic acid in the presence of concentrated sulfuric acid. So this acts as a catalyst, remember. This removes the water from the reaction and drives it forward. This is a condition, okay? So, and the condition and the reagent, but it's also showing, hey, we need to add the ethanoic acid because that's the other part of the ester we need. Now, if you didn't write that, you could have just written CH3COCl. You could ethanol chloride. That would have worked as well. That still would have produced an ester, and then you would have produced an HCl instead of a water. And here's our final product. Now this is quite a taxing question. It takes quite a bit of thinking, and you really need to get yourself in order when you're doing this. And because of that, they're going to give an excellence grade for this. So if you got one of these correct, one correct conversion with the reagent, so one of the steps correct, you get an achieved. Or you recognized, you showed from your working that you knew that the position of the functional group had to change from the second carbon to the first carbon. One of those points you get an achieved. If you got 3 steps correct, so 1, 2, 3, so you missed one of the steps, you get a merit, and if you get all of it right, you get excellence. So hey, if you keep practicing reaction schemes, they are well worth it when it comes to this paper. Okay, let's look at the next question. Okay, next question. Complicated. Yes, looks a wee bit complicated, but let's take the time to unpack it. The following table lists the structural formula of 6 different organic compounds. So they've given us, in this case, the condensed structural formula. We can see that each one of these has their own functional groups associated with them, and obviously that's going to link in to what comes in the next part of the question. So the next part of the question says, choose the appropriate organic compound from the table above to match the observation recorded from the chemical test and the solubility in water. each chosen compound number, put each chosen compound number in the table. Okay, so we've got two parts of the table we need to fill in. Okay, there are two rows. So the first one, let's look at us. So it says there are bubbles formed on upon addition of sodium carbonate. Don't get confused with an addition reaction. They've just added sodium carbonate to the sample. Okay, so and you see bubbles. So when you see bubbles, it's a carbonate. Automatically think acid. The acid is going to be a carboxylic acid. Okay, so which ones up here have carboxylic acid functional groups? Well, we have 4 and 6. So at the moment, they're the only ones that have carboxylic acid group, the C double bond OH. So one of these must be the answer. Let's use the second test they do to see if we can refine that, or if we can make, I guess, reduce this to what it is. Okay, the purple solution, we have a purple solution to brown solid upon the addition of potassium permanganate. So they added potassium permanganate, went from purple to brown. That means that we have had an oxidation of a double bond to make a diol. So that means there must be a double bond. So wait, both of these have a double bond? It could be 4 or 6. Well, remember, they told us whether it was soluble in water or not, so they're going to need us to use this physical property to distinguish between these two. Now, if you remember about soluble in water, organic molecules generally with less than 4 or less carbons can be soluble in water if they have carboxylic acid, amine, aldehydes, alcohol, sometimes ketone functional groups, right? Now these they have carboxylic acid functional groups. They could be soluble in water. However, 6 has 4 carbons and 4 has 1, 2, 3 plus another 5 here because there's 5 in the brackets. That's 9. Wait, 3 plus 5 is 8. My math isn't that good. Plus an extra carbon, that's 9 carbons altogether. There's no way this is dissolving in water 4. So this is going to be number 6 because this is soluble in water. Now, let's look and see if we can identify the next one. So the next one turns damp red, litmus blue. It must be a base. Now, the only thing that's going to turn litmus paper blue is an amine. Amides are not basic when we put them in water. They're not basic enough to change. They will possibly react with an acid. Usually they don't. They usually hydrolyze. But amines are bases, so we're looking for the amine functional group. There they are. So that's 1 or 3. Blue solution to orange when heated with phenylene solution, sometimes called Benedict's phenylenes. So that's going to be an aldehyde. Okay, so this is a weak oxidizer. It can't oxidize an alcohol. It's only strong enough to oxidize an aldehyde. Anyway, when we look at these two, this number 1 has a ketone functional group and number 3 has an aldehyde functional group. So there we go. We've worked out that the next one is number 3, but it also says it's soluble in water. So let's just confirm this. This has 1, 2, 3 carbons, less than 4, and it has an amine functional group. So yeah, it is going to be soluble in water. So here's 3. Now, the second part to this is justify why we did this. So I just went through and justified with you each of my choices, but we need to write them down. And in our answer, we should relate the observation to the functional group, identify the type of reaction involved, and account for the solubility in terms of chain length and functional group present. So let's do this for 6 first. 2 functional groups. It has a double bond in blue and a carboxylic acid in yellow here. The carboxylic acid reacts with the sodium carbonate to produce carbon dioxide bubbles. This is an acid-base reaction. Okay, so I have said the type of reaction, I've said the functional group. Now for one of the observations, let's do it for the second one. The double bond is oxidized by permanganate becoming a diol, right? True. Okay, so we've talked about a second one. Now, I didn't say this is an oxidation reaction. It is. Oxidized is kind of says that it is an oxidation reaction here. You might write this as an oxidation reaction just as a short sentence afterward. I didn't worry about it. I assumed that the marker would work that out from what I'd written. As the molecule is a carboxylic acid and there are less than 5 carbons, it is soluble. So I've explained the solubility. Okay, so remember I said if it had one of those 5 functional groups, less than 5 carbons is going to be soluble in water. So now we do the second one. Molecule 3 has 2 functional groups, amine on in the yellow here, and an aldehyde on the left. The amine group is basic, turns damp litmus red litmus blue, and the aldehyde group can be oxidized by filling solution. Again, I didn't say this was an oxidation reaction, but I said the verb, I think it is, it's oxidized, so they should better figure that out. As this molecule is an amine, has less than 5, it's also an aldehyde. So because it has an amine and an aldehyde functional group, and there's less than 5 carbons, it's definitely going to be soluble. Okay, so how did they distribute the marks for this? Okay, if you got one correct, identifies one compound correct, got the number in the correct part of the table, they gave you an achieved. If you identified, if you linked a functional group to the observation, you got an achieved. So if you said, okay, it was a carboxylic acid that produced the bubbles, achieved, right? If for compound 6, if you linked one functional group and one reaction type to stated observation, so let's say we did the let's go back to the carboxylic acid again that reacted with sodium carbonate, that what produced carbon dioxide bubbles, and that was an acid-base reaction. If you linked all 3 together, you get the merit. If you did the same for 3, you get a merit for that, right? Okay, we get that. Wow, there's a lot of marks in this question. And then finally, if you put everything together and justified it fully, you get the excellence. So it's well worth going over and reviewing the observations for distinguishing tests. Okay, well worth it. There are so many marks here. This is going to get you a long way to getting an E7 or an E8 in this first question if you get this right. And it definitely will solidify the merit grade. Okay, so in this question, this is this year, 2023. If you got 1E, so if you got this question right, you got an E7. If you got 2 E's, you got an E8. If you got 3 M's, you got an M5. So you would have got this question completely right. You've got to get a merit from one of the previous 2 I've just talked about. And of course, for N1, N2, A3, A4, it's 1 achieved, 2 achieved, 3 achieved, and 4 achieved. And remember, we're always aiming to get that E7 or E8. Sometimes we don't get the E8 because we make a little mistake. E7's perfectly fine, and we just add those up along our paper. Okay, next question, question 2. Student has 2 test tubes. One contains propane 1-ol and the other propane 2-ol. Okay, primary and secondary alcohol. The student starts. Student adds acidified potassium permanganate to each test tube and warms in water. Describe the color change. Okay, now if we saw the previous question, when we add not acidified potassium permanganate to an alkene, it goes from purple to brown. So we know that it starts purple, but guess what? It doesn't go brown when it's acidified. It goes from purple to colorless. Okay, now explain how Tollens reagent could be used to distinguish between these 2. So I used permanganate here, didn't tell me the difference between these 2. How could I use Tollens reagent to distinguish, between the products of these 2 reactions? So what is the product of propane 1-ol being oxidized? Well, it's going to go to 2 things. It will turn into propanal, and then it will continue to react on to propanoic acid unless you were able to do a distillation separation as the reaction happened. Propane 2-ol will turn into propanone, a ketone. So if we know that the first one is going to turn into carboxylic acid and the second one, oh wait, sorry, let me read this again. Tollens reagent we use to distinguish, they're just saying propanal and propanone produced in part 1. So part 1, they must have carried out a distillation, collected the propanal, right? So they've got propanal, which is an aldehyde. They've got propanone. How do we distinguish between a propanone and propanal? Well, we can either use filling solution. They already talked about that in the previous question, or Tollens. We need to remember that. Remember, Tollens solution is the silver mirror test. You add a silver complex ion, silver with that's been complexed with ammonia. You add that to the aldehyde and you heat it, and it will produce a silver mirror on the inside of the glass vessel that it's in. So what do we observe with this? Well, both samples, it's heated in the water bath. It's going to produce a silver mirror in the test tube if it's an aldehyde, and it is oxidized to a carboxylic acid. And we have to give the structure of the products. Now, the easiest way to give structure to the product, the structure of the products is really just to draw a reaction for this. So I've drawn the aldehyde on the left. I've just written Tollens reagent above the arrow, and I've drawn the carboxylic acid on the right. Now, I know that you might have seen more complex reactions to do with a Tollens reagent, where you have the silver ammonium complex on the left and the silver metal produced on the right. However, in this case, this is all that's needed. It says a structural formula of the organic product. So I've done a simple reaction here. I've written the type of reaction, oxidation reaction, even though I've got the verb oxidized up here. Wait, is that the verb? Yeah, I think it is. It was an adjective. I'm not an English teacher. We write oxidation here. The ketone can't be oxidized. So I'm saying, okay, the ketone can't be oxidized, so propanone will not form a silver mirror. That's how we tell the difference between propanol and propanone. Okay, so how did they answer this? So, excuse me. If you had correct observation for both alcohols, that's purple to colorless, or correct observation for Tollens reagent, you get achieved. If you explained how Tollens reagent can be used to distinguish between propanol and propanone with the structural formula product, you're a merit. This is a merit question. Okay, part B. It says that C4H5O2Cl can exist as a number of different constitutional isomers. Now remember, constitutional isomers have the same molecular formula. They just have their bonds attached in different ways, right? So we need to draw the structural formula of C4H5O2Cl that have the properties that they state. So the first one is a straight chain molecule. Now what a straight chain molecule, how it is different to a branch chain molecule, is a straight chain molecule is each carbon is joined to the next carbon after it in a chain. There are no branches coming off, or there are no pieces coming off. You haven't got a CH3 coming off. So I've got to have 4 carbons in a row bonded to each other in sequence. It turns damp litmus paper red, carboxylic acid, okay, right, or an acid chloride, so it's going to be either, and rapidly turns bromine water from orange to colorless. If it rapidly turns bromine water from orange to colorless, it's got to have a double bond or a triple bond. Usually when we're doing these questions, it's a double bond. So here is my first example of the molecule. Now, stay with me here. So let's see if this meets all the requirements. Does it have enantiomers? Right. Does it have enantiomers? Does it have a carbon that has 4 different groups coming off it? Yes, it does. This carbon, the third carbon along, has a hydrogen, a chlorine, this carboxylic acid group on the right, and this double bond on the left. So it has 4 different groups. Fantastic. Will it turn litmus paper red? Yes, it will. And because it has the carboxylic acid functional group on the right, will it rapidly turn bromine water from orange to colorless? Absolutely, because it has this double bond. So it meets the requirements. Now remember how I said that maybe an acid chloride would turn the damp litmus paper red? If I'd put the chlorine here and the hydrogen off the third carbon, that still would have turned damp litmus red, and it would have reacted with bromine water, but it wouldn't have had an enantiomer. It wouldn't have been an enantiomer. It wouldn't have had a chiral carbon. So that's why I decided to go with this structural formula. Oh, here's those are the 4 different groups, atoms that are coming off my chiral carbon. Okay, and I've highlighted here the red carboxylic acid and the part that reacts with the bromine water. Okay, so let's look at the next one. The next one, I said it needs to undergo hydrolysis in acid conditions to produce methanol. So it's got, I've drawn this ester group here because it's going to produce a methanol, so it must have originated from an ester group. Also must have this CH3 joined to the oxygen here in order to make methanol. exist as a cis-trans isomer. Okay, this can exist as a cis-trans isomer because it has a double bond. Okay, and here we go. The carbon of the double bond, each carbon of the double bond has two different groups or atoms coming off it. So we have two different on the left-hand one and two different on the right-hand one, and that's why it's geometric isomers. So these are the two isomers we possibly could have drawn. If we identified two correct functional groups from the data we're given, we're achieved. Notice again, this is observations for distinguishing molecules really. So if we'd learnt this up, what we did on a previous question and this question, we would have been helped in both of them. If we got one structure correct and at least one correct functional group for the other one, we get a merit. And if we get two of these correct, as I've drawn them, you get an excellence. So yeah, these are, starting from scratch, they're quite challenging. They are a problem, they're a jigsaw. But hey, if you can get confident and good with this, and you will start to do really well in the paper. Okay, so next part here, we have a dipeptide. So remember that's two amino acids joined together by an amide or a peptide bond. So we need to draw the structural formula of two amino acids used to produce it. So in our cells, in our body, we would produce this dipeptide. What are the two amino acids that would do it? So we have to recognize that here is the peptide bond or the amide bond. And when this was formed, the two original molecules would have been split on the right-hand side molecule and the left-hand side molecule here. Now remember, when we produce a peptide bond in a biological system, we start with a carboxylic acid and an amine. So this C double bond O here was a carboxylic acid and the NH was an amine. So we're just going to separate these two molecules. We're going to replicate them, draw them again on the piece of paper, and we're going to add the bits that are missing. And here we go. So I've just drawn the left-hand side, and I put the OH here that was removed when it was the peptide bond was formed. And then on the right-hand side, I'm going to do the same, add the extra hydrogen that was removed when it was formed. Now notice these are called amino acids because they contain an amine and an acid, an amino acid. Technically, to be an amino acid, the amine and the acid has to come off the same carbon. Okay, so this amine at the bottom of the second amino acid is an amine group, but it isn't what makes it an amino acid. So identify and explain the type of reaction occurring, the formation of the dipeptide from the two amino acids. So if we took these, we put them together, what type of reaction is it? That we could call that a condensation reaction, right? Because two smaller molecules are combined to make a larger molecule where a small product is removed, water in this case, and an amide or a peptide bond was formed. Remember, what's important, two smaller molecules are combined and a small molecule is removed. Okay, so we draw the formula of two organic products formed from acidic hydrolysis. So if we split these apart, these are the two molecules we would produce. When we say acidic or basic, it's not, it doesn't really, that doesn't change them breaking apart, but when the molecules are sitting in the acidic conditions, what happens is the base part of the molecule react with the acid and accept a proton. If we put them in base conditions, the acid part will react with the base and donate a proton. But we're in acidic conditions, so this part here, the amine part, and the amine part at the bottom is going to accept a proton from the acid conditions it's in. So when we redraw this one on the left-hand side, the amine is going to have an extra hydrogen and an extra positive charge. So it's going to look like this. That's NH3 plus or H3N plus, right? So we're going to do the same for the one on the right, but it's not just the amine that's associated with amino acid that's going to be protonated, it's the bottom amine as well. So it's both amine groups, right? So I've drawn both of them here. They're both protonated because they underwent acidic hydrolysis, they're sitting in acid, and they get given that proton from the acid. Okay, so did you give two correct structural formulas of amino acids? So if you're able to draw them, that's an achieved. And identified condensations. You just had to write condensations. You needed both. That's a bit more challenging to achieve than what we'd had previously. If you can explain what a condensation reaction is, that's when we join two smaller molecules to make a larger molecule, and a small molecule like H2O or HCl is produced. Merit. If you protonate one of these amino acids at the bottom, they give you an achieve. But if both molecules have one amine, so this is kind of weird. Okay, so if you protonated one of these, achieve. If this is protonated, the amine here, and only one of the amines is protonated, you get a merit. But if you remembered to protonate all of them, that makes you exceptional, and you get an excellence. Well done, you. Okay, so this is marks very similar to the last questions. Okay, 2 E's, E8, 1E, E7, 4 M's, M6, 3 M's, M5, and then we've got 1, 2, 3, 4. A's are N1, N2, A3, and A4. Okay, let's look at the last paper. Question, not paper. Okay, complete table below to show the structural formula using the IUPAC systematic name for each molecule. Don't be scared by them using this acronym IUPAC. It's just the International Union of Physical and Applied Chemists. They are not scary. They are not looking over to take over the world. They are just the people who get together and say these are the naming rules we're going to follow. So we call it the IUPAC naming system. Okay, so we have pentan 3-one. I drew 5 carbons in a row because it's pent. And off the third carbon, I put a double bond, right? Because it's pentan 3-one, double bond oxygen. Okay, for the second one, we can see that this is an ester. I'm going to break it here. It has a piece on the right-hand side and a piece on the left. The piece on the right-hand side is the alkyl group, and it's the first part of the name. So this is going to be ethyl. And on the left-hand side is the NO8 group, right? And so there's 3 carbons, so it's propanoate. So it's going to be ethyl propanoate. Ethyl propanoate. This one here, the next molecule, we can see that there are, how many carbons? 1, 2, 3, 4, 5, 6 in a chain. And it has the acid chloride functional group on the end, so it's going to be anyl chloride. Okay, so hexanyl chloride, but there's a chlorine. Now, we need to remember that this chlorine is off the 4th carbon because we always start our numbering from the functional group on the end. If it's carboxylic acid, if it's an amide, or if it's or aldehyde and a acid chloride, that starts as number 1. This must be 4, so this must be 4-chlorohexanyl, 4-chlorohexanyl chloride. Last one, 2-methylbutanamide. Anamide means there is an amine group on the end. 2-methyl means we start counting from that end and we put a methyl group off the second carbon. And here we go. So that, now, notice when I draw them, if I was doing the paper, I would draw them out fully drawn, not condensed. Now the reason I do that is just to make sure that I don't miss one of the bonds. I might have put a CH3 instead of CH2 or CH2 instead of CH3, but if I show each of the bonds represented, I'm pretty sure I'm going to get it correct. Okay, answers. If you got 3 correct, achieved. That's it. So it's just an achieved question. Okay, triglycerides are found in fats and oils, sometimes called triesters. Complete the balanced equation. Oh, look at that. It's been highlighted balanced. What does that mean? You're going to make sure that the whole equation is balanced, and you're not going to get the full mark if you don't. Show the basic hydrolysis of the triglyceride, of this fat, using the structural formula for organic products. This is actually stearic acid, the bits that are coming off here. So this is most probably beef tallow, or this is fat that you would find in cattle. Anyway, so basic hydrolysis, we are going to break, hydrolysis is to break the ester bond or the amide bond if it's an amide, remember. So we're going to break it right in the middle here, and because it's a basic hydrolysis, I'm going to use sodium hydroxide, aqueous. Okay, so it's going to be dissolved in water, or I'm going to use potassium hydroxide. In this case, I just chose sodium hydroxide. Now, remember how it said balanced. Every one of these OHs that are being used here, I need one for each break that I do. So if I'm going to break 3 of them, I'm going to need 3 sodium hydroxides. Okay, so I then show what the products of this is. So remember, I broke it here, here, and here. So I'm going to end with what's on the left-hand side. So this is going to be the alcohol. Each one of these O's is going to grab an H, and this is going to be glycerol, or 1, 2, 3. Not 1, 2, 3. This is pentan 1, 2, 3 triol. Okay, and we produce one of these, and then we produce this molecule here. So remember, we're breaking this ester. This is a carbon double bond O. It's going to get an OH, so it's going to become a carboxylic acid. But right, it's in basic condition, so it donates its proton. So we can either draw it as the carbonate ion, okay, like this, and we need to have 3 of them because there were 3 of them broken apart. Okay, that's it, balance. Now, you might draw it this way. Lots of people like to draw it this way, where they say, oh, well, there was a sodium, we're just going to put the sodium next to it. I just draw it usually myself with the sodium not included, but if you do it that way, you've got to remember to put the negative charge. Okay, which one of the following pieces of equipment would you use to carry this out? Well, this isn't a distillation. This is a straight, we're just putting in, we are heating it up so it reacts, right? So we need the temperature for the reaction to happen quickly to speed up the reaction, but we don't want to lose any products. A, distillation. B is separation. Sorry, C is separation, so we're going to use B, which is a reflux. So we select B. The reason is the high temperatures needed for reaction to occur quickly in a reasonable time. So I should have maybe said something about speed there. And the condenser will collect any volatile products. I can't see any volatile products. I mean, glycerol might be volatile once you get up to about 300, 400 degrees Celsius. But it would be used, if anything, if you did have a volatile alcohol coming off and you needed that in your yield, what would happen is the condenser would collect it and they would fall back into the flask. Okay, so if you added a strong base here, right, and one of the products correct, you got it achieved. If you bought the correct structural formula for both products, you got a merit. If you balanced the equation, they gave you the E. So that's the balancing the equation part. I bet you a lot of people just missed that highlighted bit there, but don't make it you. If you select B here, correct. If you said B with 2 valid reasons, they gave you an E. I'll double check that. You maybe should double check that. There might have been a merit. That's hardly an E, but that there is right. Okay, so last question. If you look at this question, if we just scan it for a start, we can see that there's 4 compounds. They want us to draw compound C, D, E, and F. And what they've done is they've given us some properties of the compounds and they've told us some reactions that they undergo. So let's start with compound C. Say compound C is a branch chain molecule. Now they've given the molecular formula C4H9O3N. If it's a branch chain molecule and it has 4 carbons, the only way you can draw a branch on 4 carbons is to have 3 carbons in a row with a methyl group coming off the second carbon. So that's going to be the framework for this molecule. Okay, so you're going to draw 3 carbons in a row with 1 coming off the center. Then the second thing it says is it has enantiomers. That means there must be a chiral carbon, so one of the carbons in that position. So my guess is it's the second carbon that has the methyl group coming off. That must have 4 different groups coming off it, which means we can't have 2 identical methyl groups coming off. So we just need to look at, when we draw that, look out for that. It says that it undergoes acidic hydrolysis to produce compound D. Now, acidic hydrolysis to compound D, let's look at what compound D reacts with acidified dichromate to produce compound E. Both compound D and compound E, so here's more information about D, turns blue litmus red. So compound D must be a carboxylic acid. So however we draw C, we need to ensure that when it undergoes hydrolysis, there is going to be a carboxylic acid functional group. So here's what I've done. I've drawn 3 carbons in a row with a carbon off the middle. I have ensured that I've got 3 oxygens here. Now, because it isn't a hydrolysis, I know it's either going to be an ester or an amide group. I know it's not an ester because in order to be an ester, I would have to have 3 carbons on one side of the carbon double bond oxygen and 1 carbon on the other, and it wouldn't meet the requirements of being a branched chain molecule. So I ruled out that it was an ester because you can't have a branched chain molecule with 4 carbons and be an ester at the same time. So I ruled that out. So therefore, it must be, if it's going to be hydrolyzed, an amide, it must be a primary amide, right? So we've got a primary amide. So this can be hydrolyzed under acidic conditions. That means that the NH2 is going to be removed and OH is added here. Now, once I've worked out that this functional group is an amide, I have 2 oxygens that I need to add. I can't add a double bond between the carbons on the left because it wouldn't have a chiral carbon anymore, so they must be single bonds. So I've drawn them as alcohols, and let's just check whether this makes sense. If I added acidified dichromate, would this produce a carboxylic acid? That is, because D turns blue litmus red. Yes, it would. The alcohol group coming off the first carbon would turn into a carboxylic acid and it would be acidic. So I'm actually quite happy with compound C as it is. It's got something that can be hydrolyzed, it has optical isomers, and it is a branched chain molecule, so it meets all 3 of those requirements. So if I undergo oxidation with acidified dichromate to make compound D is if I hydrolyze this, to make compound D, so I'm going to hydrolyze this. If I add H3O plus / water or water H3O plus, then I'm going to produce this here, this carboxylic acid group on the right, okay, and compound D will make blue litmus go red because it has this carboxylic acid, so that's an okay for compound D, but compound D can now react with acidified dichromate to turn into compound E. Now, if I add acidified dichromate to this molecule, it's going to do nothing to the carboxylic acid functional group. It will do nothing to the OH off the second carbon because the second carbon here, the OH is a tertiary alcohol, right? It's joined to a carbon that itself is joined to 3 other carbons. So this is a tertiary alcohol. It can't be oxidized. But the alcohol group off the third carbon here, 1, 2, 3, is a primary alcohol, so it can be oxidized to a carboxylic acid, or it could be oxidized to an aldehyde. Here, I'm going to draw it being oxidized to a carboxylic acid. The alternative is you could have just drawn an aldehyde as a functional group on the left-hand side, and that would have been perfectly fine. Okay, so the last bit, it reacts with excess thionyl chloride to produce compound F with steamy acidic fumes. Okay, steamy acidic fumes, we've added a chloride, we know we're producing an acid chloride. In this case, because I have 2 carboxylic acid groups and I have in excess, that means I have all that I need. I'm going to change both functional groups to acid chloride groups. So these are both going to be acid chloride groups. The other thing I'm going to do as well is I'm going to substitute the alcohol with the chlorine, because this SOCl2 will both substitute alcohols and it will substitute the OHs with the chlorine on carboxylic acids. So we get this molecule here, which looks kind of complicated. So how do the answers work here? Well, compound C, if you drew it as that it does have a chiral carbon, that does have enantiomers, and it can undergo hydrolysis, which this is. So you might have done it wrong. You might have drawn an ester group, but you had a chiral carbon as well. I don't know how you would do that, but anyways, let's say you did, you got an achieved. Or let's say you just draw the chiral carbon, but you didn't put the extra OH, or you did a bit different. You could get an achieved there. If you got compound C correct, because it was quite complicated, quite a bit of thinking around this, you got a merit. if you did 2 correct conversions of functional group between compounds, so let's say you got compound C entirely wrong, but then you did hydrolyze it to form compound D, you get an achieved. If you do 2, so you would also have to do an oxidation or a substitution on the final reaction. If you did 2 correct conversions from a correct C, so you did 2 steps correctly, let's say you didn't do the last step and substitute all of the OHs, then you're a merit. Or 2 structural formula correct from minor error in C. So if you made a minor error here and 2 of the others are correct, you can get a merit. If you 3 correct structural formulas, you don't actually have to get all 4 correctly in this, because it's such a tricky question. So let's say we didn't substitute all the chlorines in F, but everything else was right, you're still going to get the excellence. Okay, so if you did a minor error in the first one, okay, so it could be to do with maybe the OH coming off here at the bottom, you might have just put an H or something, and then everything else was correct, you can still get an excellence. So how does this work? So you, in this case, in this last question, you need 2 E's to get an E8 and 2 E's with a minor error to get an E7. So it's a wee bit different than the first 2 questions. 4 M's for an M6, 3 M's for an M5, and then 1, 2, 3, and 4 for N1, N2, A3, and A4. This is the last question, so what we do is we take what we got from each one of the 3 questions and we add them up. And if you got less than 8, you didn't achieve. Keep trying though. If you got 8 to 13, you're at achieve level, 14 to 18 a merit level, and 19 to 24 excellence level. Look, I would, if you look at this question for 2023, a lot of what you have to do is looking at the functional groups and the properties and how you distinguish them. And once you have a good handle of the functional groups, you can answer a lot of the questions to merit and excellence level, and that will get you to the point. And once you have a good understanding of the functional groups, you understand how to change between them, you can write reaction schemes. So actually, to do well in organic chemistry, you just have to dive in and have a go at learning all of the associated properties and reactions of each functional group, and that will get you there. Okay, hope you have found this video useful. Look out for the other videos that I've done. I will be uploading a video later today on achievement standard 91392. That's aqueous chemistry from 2024. Good luck.